Oh, welcome to number theory. So now that we have discussed the syllabus, let's go ahead and get started on the first lesson of the course, specifically what are the assumptions on the numbers that we will be assuming throughout the term. Now, before we get started with the content, I want to go ahead and just make a comment on the lecture notes. So on Moodle, you'll be able to find this document. It's a PDF. And so in it, you'll be able to find from what I will be lecturing on. While I'll be following the book closely, the first 2 weeks of the course, or specifically the first 6 lessons, assumptions on the integers, all the way to arithmetic with congruences, I will be mostly lecturing from the lecture notes rather than the textbook for one reason. The textbook that we have, while it's good on the second half, the first half was initially written as a book to learn how to write proofs. And so specifically a secondary book for structures without going into the topics of infinity that we cover in our course. As a consequence, the first 5 to 6 chapters of the book have much more detail in that they're setting up induction, getting familiarity with induction, than what we will need. And so I'll be taking a path of least resistance to get us to the fundamental theorem of arithmetic, which is here in the lecture notes, lesson number 5. And so this is the theorem that states that if you have a natural number, then it factors uniquely into a product of primes, up to order, of course. And so that's just a small note just to be mindful of, is that the first 5 weeks, the textbook will rarely be used except for the homework assignments. I do encourage you to still go through the book, and at times, especially once we get through the first 2 weeks, but any result that I have in the lecture notes that is also in the textbook. So for example here, this lemma 1.2.1, this is the labeling in the lecture notes. In the textbook, this corresponds to lemma 3.1.2. Similarly, you'll have like theorem 1.2.3, so the label is now with the section. This is the first lesson, but then this corresponds in the textbook to 3.2.5. In the lecture notes, I sometimes go ahead and put these comments in brackets. So you'll have a bracket over here, which will just be some commentary on the proof. Now, in the recordings, I will be going through the lecture notes almost, following them almost identically. The one caveat, of course, is that in the lecture notes, the proofs are written to completion, whereas sometimes due to the interest of time in the video, I may use shorthand notation or talk about the main ideas and sketch the argument. And so I highly encourage you to have the lecture notes at hand as you watch the video if you want to go in and see a specific detail that I may have glanced over. Although I do not expect it to be that prevalent. But it's just something as we go into some of the more involved proofs, some of these, to go into detail that's in the lecture notes, would take the whole lesson. And since we have quite a bit of material to cover, I will have to make some sacrifices in terms of the presentation. And so I may choose to go with a intuitive or sketch of an argument rather than the full argument of setting everything up. And so just something to be mindful of. In the lecture notes, you'll have all the details. And so it's worth going through and having that at hand as you're watching the video. Okay, so with that, let's go ahead and get started with the assumptions that we will have in this course. And so let's start off with definition. So depending on when you took structures, the natural numbers may have been defined differently. So here the natural numbers are the numbers we use for counting. So 1, 2, 3, 4, 5. So in other words, 0 is not a natural number in this course. Now, this is something to be mindful of as you go from course to course. In some texts, 0 is considered a natural number. And so if you took structures out of Galovich, 0 is considered a natural number. In number theory, however, we do not consider 0 to be a natural number, since its history actually is quite interesting in that it's a very recent concept. If you go back to ancient Greece, they did not have a concept of 0. In fact, it was not until 1598, in Western culture at least, that 0 was actually used as a number. So mathematically, is a quite recent phenomena, just over 400 years. That being said, in India, Pingala came up with a concept of zero. And so we'll be talking about Pingala to some extent in some of the lessons coming up, in that he developed actually his motivation was in poetry and Sanskrit, but he developed the binomial coefficients, the numbers that appear in Pascal's triangle. And so we'll touch upon that when we talk about Fermat's Little theorem. Okay, so we have the natural numbers. Just keep in mind, we're just counting 1, 2, 3, 4, 5. The integers are those numbers, including 0, the natural numbers, and the negative natural numbers. So here we have -3, -2, -1, and then we just go on and on. Now, the rational numbers is the next set of numbers that we are going to be looking at. And so those are the ratios, a over b, where a and b are integers, and b is not equal to 0. Now, a comment on this set. This is actually wrong, but it'll be fine for our purposes. So why is this wrong? Well, if we go about it from the point of view of structures, we have a set, and so according to this definition, 1/2 is in Q, but so is 2/4. But are 1/2 and 2/4 equal? Well, in Q, by the definition, (1/2) and 2/4 are distinct elements. So, in other words, 1/2 does not equal 2/4. The precise way of defining the rational numbers in mathematics, from the language of set theory at least, is by considering an equivalence relation. So instead, we can look at the integers, the Cartesian product of the integers with itself, so z2, and we can define a relation. And we are not going to be using this through the course. This is just for instructional purposes to see that we can define, set theoretically, the rational numbers rigorously. So we can define a comma b. So these are in the integers Cartesian product with itself. So this, remember, this is z cross c Cartesian product z. So with this terminology, we can define a comma b to be related to c comma d if and only if AD is equal to BC. And the precise way of defining the rational numbers is as the collection of equivalence classes on this. So we have a comma b, tilde for the equivalence class under this relation, let me just write it like this. So we have this here. So this is the collection of these elements. Or in other words, we can write this as integers Cartesian product, integers modulo the equivalence relation. And so this is a precise way of rigorously defining the rational numbers. But again, this is just to showcase that we can define these things in the language of set theory. Before we continue, let's just go back over here and just do a quick double check. So we have 1/2 and 2/4 in this now both of these are in the same equivalence class. So I'm going to come up over here and say we have 1/2, which I'm going to look at as 1 comma 2. This is the same as 2 comma 4 under the equivalence relation, which we did not show as an equivalence relation, but this is not so hard to show. So I leave this as an exercise if you want to verify that this is in fact an equivalence relation. So we take A, which is 1, and we take D, which is 4. So we have 1 times 4. And then we can check that this is equal to B, which is 2, times C, which is also 2. And so we do get 4 is equal to 4. So both of these elements are in the same equivalence class. And so the rational numbers rigorously is a collection of equivalence classes, and then we define addition and multiplication on equivalence classes. While we will not be using this notion in the course as I mentioned, when we talk about modular arithmetic, so the integers modulo n, we will actually be defining addition and multiplication on the set of equivalence classes. And so we'll come back to these sort of ideas in a couple of weeks. Now, the real numbers are not going to play a role in this course. And let me just create a new slide. Okay, so the real numbers, we're not going to really be focusing on in this course, but the symbol for the real numbers is the bold-faced R, so denoted like this. Another set of numbers that we're going to be looking at subsets of later on is the complex numbers, or as they are commonly referenced, the imaginary numbers, where we talk about I as the square root of -1. As a historical context, the reason for the word imaginary is that René Descartes, who gave them the name, felt uncomfortable with them, and he called them imaginary, and the name stuck. Now, we will be looking at subsets later on for the complex numbers, but the important one that we want to look at is the irrationals. And so this is the set of real numbers that are not rational numbers, so the square root of 2. And later on we will prove a statement that was also proven in structure, specifically the square root of 2 is irrational. But we will go one step further and prove that in a more general context, where we will get irrationality for not just square root of 2, but many other irrationals that we know. Now, in the same way that I made the fuss about the rational numbers not being a set in this notion, and then we had to go ahead and define it, the real numbers, defining this rigorously takes quite a bit of work. And if you take a first course in real analysis, the first couple of weeks, or actually the first few lessons, are devoted to proving rigorously that what the set of real numbers is and how it looks like. And then complex numbers has it much easier, because since we can assume real analysis, we know that the set R already exists, so we can say that it's just a collection of elements, A plus BI, where A and B are real numbers. Now, this idea of set theory and defining things as sets, which is how modern mathematics is defined today and built upon, is actually a rather recent notion. As you saw in structure, set theory did not come about until 1874 with George Cantor's work. Now, prior to that, mathematicians still used definitions like natural numbers, integers, rational numbers, of course, but they didn't think about it as a set. So the notion of a set is a more recent concept. And following Cantor's work in 1874, a lot of many mathematicians began to focus on rigorously defining arithmetic in the purview of set theory. So only assuming the basics of set theory can one axiomatically build up the natural numbers and give it a foundation. And so this was Gottlob Frege's dream. And he worked on this for 20 years. He worked at constructing, based on set theory, an axiomatic system that would be able to prove the result in arithmetic. And so essentially, by writing it in the language of Cantor's set theory, we would be able to axiomatically build up the whole topic and no longer have to rely on intuitive notions. And that's the idea that made set theory very powerful, and to this day it's a powerful topic, and we build everything on set theory. Prior to Cantor, lots of arguments were intuitive. And the consequence of arguments being intuitive, because they did not have this rigorous foundation, is that there were theorems that were proven that were actually found to not be theorems later on, because there were errors in how mathematicians approach the argument. Because by basing it on intuition, oh yeah, this seems to be true, so it should hold true for sure. And errors then followed. And this is true of Frege's work. He worked on his book, which is over here, the Foundations of Arithmetic, for 20 years to rigorously found arithmetic. And he had a specific rule in one of his axioms that he had developed. And that rule was, that if you're given any collection, there's always a set containing them. So if you're given some objects, there will be a set that contains those objects. So if we have a collection of chairs, there's a set, abstractly of course, that contains those chairs. And that was one of his building blocks for his theory of arithmetic from set theory. Unfortunately, when he submitted this for publication, it was found by Bertrand Russell, who was the reviewer, that rule of 5 is not true. And in structures, you saw Russell's paradox. And so what Russell's paradox says is, what if we consider the set of all sets that do not contain themselves? And so symbolically is what we have here. We have S such that S is not an S. And we have a problem, because if we ask, well, is the set R in R? So if R is in R, well, what does that mean? Well, this is telling us that if we are in here, so if R is in R, then we have a problem, because to be in the set, we cannot contain ourselves. So if R is in R cannot be in R. Well, that's a big problem. What if we do it in reverse? So that must mean that R cannot be in R. So if R is not in R, then looking at the definition of what it means to be in R, it's those sets that do not contain themselves. But we already have that condition. R is not in R, so R must be in R. But this is also contradictory, because now we have R not in R implies R is in R. But up here we had R is in R implies R is not in R. So we have a contradiction. So in other words, this collection, even though we can write it, it is not a set. And that's what Russell's paradox gets at, is that if you're given objects, it is not the case that there is a set that contains those objects. And this was the nail in the coffin for Frege's work. But Frege responded graciously to Russell. So Russell wrote to Frege, informed him of what now is known as Russell's paradox, and how in an unfortunate circumstance it just derailed all of Frege's program. And so Frege responded, "Your discovery of the contradiction caused me the greatest surprise, I almost say consternation, since it has shaken the basis on which I intended to build arithmetic. It seems, then, that transforming the generalization of an equality into an equality of course of values is not permitted, that my rule of 5 is false, and so this is a given collection of objects, there's a set that contains them, and that my explanation in section 31 are not sufficient to ensure that my combinations of signs have a meaning in all cases." One of the apocryphal stories revolving this letter of Frege to Russell is that prior to Frege writing it, he spent a month essentially having a mental breakdown, since his life's work was essentially brought down to nothing by this construction, which he had failed to see. But he, once recovered, responded graciously, and so he mentioned, "I must reflect further on the matter. It is all the more serious since, with the loss of my rule 5, not only the foundations of my arithmetic, but also the sole possible foundations of arithmetic seem to vanish. Yet I should think it must be possible to set up conditions for the transformation of the generalization of an equality into an equality of courses of values, such that the essentials of my proof remain intact. In any case, your discovery is very remarkable and will perhaps result in a great advance in logic, unwelcome as it may seem at first." And let's focus on this aspect here, because that's the next thing I want to bring your attention to. So this is so true, and that while at first it was an unfortunate circumstance that it was just not true, but this is the things with mathematics. We want to make sure that everything is rigorous, that nothing is left to chance. And that observation that rule of 5 broke down led Russell, along with Alfred Whitehead, to work on fixing Frege's arithmetic, and they came up with what is known as the theory of types. Now, this is a monumental work. This is Principia Mathematica, same name as Newton's Principia. And in this work, Russell and Whitehead worked at, so Russell's on the left, Whitehead's on the right, they worked at overcoming the difficulties that were presented to Frege. But to overcome the rule of 5 problem led to a monstrosity of a work. But they succeeded, and one of the consequences of their work is that you can prove in the language of set theory that 1 plus 1 is equal to 2. It took them 367 pages. And here is a snapshot of the argument as it ends. And so from this proposition, it will follow, when arithmetical addition has been defined, that 1 plus 1 equals 2. And the reason I have mentioned all of this is to emphasize that when we talk about number theory and the foundations, we can go very deep, as is illustrated by this work of Russell and Whitehead, but that's not the purpose of this course. Instead, we're going to be approaching number theory from the notions that we have come to expect and the properties that we know are true. Commutativity, associativity. These things we're going to take for granted as axioms and then build our topic from the ground up. But if you're curious on seeing how this theory develops in a more rigorous approach, I want you to be mindful that you can do that, and this is a course in logic or set theory that will come with build up these foundations. Now, before we go on to I went a bit too fast. Joke about Principia Mathematica, because it's a very terse book, as you can imagine, over 300 pages to prove 1 plus 1 equals 2. So one of the jokes revolving this work is that only 3 people ever read it, namely Russell and Whitehead, the authors, and the next is Kurt Gödel, who is famous for his incompleteness theorem, which was in many ways due to his observations of all that Whitehead and Russell developed. Now, fun fact, Kurt Gödel was actually one of Einstein's best friends. They were both at the Institute for Advanced Study at Princeton. So here's a picture of them together. And Kurt Gödel's incompleteness theorem, published in 1933, there's 2 of them, but I'm going to go ahead and give you sort of a watered-down version of what they essentially imply, is that any axiomatic system from which arithmetic can be deduced will have undecidable statements. And you saw one of these statements in structures, the continuum hypothesis. So specifically, if we consider the cardinality of the natural numbers, so this is countable, and oftentimes this is noted as aleph naught. So Hebrew letter for aleph. And the real numbers is uncountable. And so we could ask, is there a cardinal number between them? So does there exist, so my backwards E for there exists, a cardinal number let's call it omega, such that aleph naught is less than omega less than aleph 1. In other words, is there a set that is of infinite size whose cardinality is between aleph naught, countable infinity, and the uncountable infinity, but it's neither in one-to-one correspondence with the real numbers, in other words, equinumerous to the real numbers, nor the natural numbers. And this is one of those questions that turned out to be proven to be undecidable in 1964 by Paul Cohen. Now, the continuum hypothesis has a rather interesting history in that essentially any mathematician that tried to rigorously work through it to prove it ended up at some point going insane. And so Cantor is usually the one that's brought up. Kurt Gödel, who proved the incompleteness theorem, also worked at it and unfortunately suffered from mental illnesses later on in his life. And once his wife died, he had already become paranoid to the point where he will only eat food if his wife tasted the food beforehand because he was afraid of being poisoned. And so in a sad tragedy, once his wife died, he starved himself to death because he was unwilling to eat, because he expected that any food that he got would be poisoned. And so the continuum hypothesis, these are just two stories, Cantor, Gödel, but it really has a tragic story in terms of the mathematicians that actually worked at solving it. But it's one of those statements that we are unable to prove whether such a cardinal number exists or not. To make matters worse, we can develop our axiomatic system to assume that there is one and everything remains consistent, or take the negation of that statement that there is not a omega in between and the system also remains consistent. And so that's just a little side story for you all. Now, if you're curious on learning more on the history, I highly recommend this graphic novel, Logicomics. So I would say as an undergrad I read this, and I learned more history from this graphic novel than I did in my undergraduate courses. And so I highly recommend it. It follows the life of Bertrand Russell. And it takes some creative freedom. It puts Bertrand Russell in some points in history where he actually was not, for the purposes of putting the mathematical culture and the culture and philosophy as well in a better perspective. And so Russell meets Cantor, which never happened in this novel. And in addition to his mathematical works, Russell is a renowned philosopher, also the doctoral advisor of Wittgenstein. So I highly recommend reading it. It's a great short graphic novel. All right. So last thing, before we get started to what we will actually assume, Russell and Whitehead's theory of type was overkill. Like I said, the running joke, only 3 people ever read it. There is an axiomatic system upon which modern mathematics is built on. And this is the Zermelo-Franco axioms. And if you take a course in set theory, this is the axiomatic system that you will actually develop. And with this, you can prove the existence of the natural numbers. You can prove their commutativity, their associativity, the properties that we will just take for granted in this course. And so this is usually denoted by CF for the Zermelo-Franco, or CFZ for Zermelo-Franco with the axiom of choice, which is covered in structures. And so these are the axioms as stated. If you're curious on this, I highly recommend Paul Hammel's book, Naive Set Theory. And so this is a text if you're interested in learning more about the foundations of mathematics from the Zermelo-Franco point of view. Naive Set Theory is a great book. It covers, as Paul Hammel states, all the set theory that a working mathematician needs to know. Because of course, logic, set theory are a branch in themselves, and one can go much further. But in terms of just the foundations, this book has it all. So let's start with what we will be assuming. And this is actually taking a very recent approach in terms of the timeline. And we're going to be defining what is known as a ring. Now, for context, a ring was not defined until 1907, and then later by Emmy Noether, who single-handedly developed what is now known as commutative algebra. And so here she is pictured. And so she is the one whom we attribute these definitions to of a ring. And Emmy Noether's approach was, there's all this mathematics that has been done for the numbers, or things that look like numbers. And as we go through the course, you'll get an emphasis for what I mean by things that look like numbers, since we can abstract these notions. And she took an abstracted point of view and said, well, what if we only look at the properties, the core properties that define the integers, and study them abstractly? Not as the integers, but as a set that has these properties. What can we prove? And so this is the foundations for now abstract algebra. And in the context that we are going to be covering it here, commutative algebra, where we assume commutativity. If you take abstract algebra, you will cover a ring, but in a more general setting. I'm taking a more, this definition of ring is not what is covered in abstract algebra. It's actually, this is a much weaker variant because I'm imposing more conditions. But since we're dealing with number theory, it will be fine for our course. But just keep in mind, when you get to abstract algebra, you won't have commutativity. That is not going to be in the axioms, nor will you have identity. So these two axioms are usually not covered in a first course in abstract algebra, where when you cover rings, they may not have a 1. They may not be commutative. But again, for our purposes, this is what we will be assuming. And so what a commutative ring is a set R together with two operations, multiplication and addition, and they satisfy the following axioms. Associativity is the same associativity that we are used to for adding numbers. If we add two numbers and then add a third, the order does not matter in how we add. Commutativity, the order in which we add, does not matter. We always have an additive identity, 0. Anything plus 0 returns the same number. Additive inverses is the negative. So here we have, if we have x, then negative x is also in the ring. And then we have the property that if we add x plus its negative, we get back the additive identity. Then we have the multiplicative properties. If we have three elements, x, y, z, and r, we multiply them. X times y times z is equal to x times y times z. The order does not matter in how we multiply. We are assuming commutativity, so x times y is equal to y times x. We have a multiplicative identity, namely 1. Anything times 1 gives us back itself. And then the last one is the property that relates addition and multiplication together, namely distributive property. So if we multiply x times y plus z, the x distributes over. I should also mention that we're going to be studying the integers, but the complex numbers, the real numbers, rings of polynomials, these are all examples of rings. And actually, in Emmy Noether's honor as the discoverer of these properties and their generalizations, as she literally single-handedly built the whole topic from the ground up. The rings that satisfy certain properties, including the integers, real numbers, complex numbers, these are known as Noetherian rings. And so if you take a course on commutative algebra, Noetherian rings are the object of study. There's also non-Noetherian rings, which are where, unfortunately, things that are highly unintuitive start to pop up. But the Noetherian rings are the nice ones. And the reason they're called Noetherian rings is that this is exactly what Emmy Noether did. She realized that there's no need to study the real numbers, the complex numbers, polynomials all separately, when you can just bring it down to their basic axioms and study only the axioms and then build everything from there. And so the rings that she studied, which encompass all the objects that we have studied up to this point, came to be known as Noetherian rings. Alright, so here is the main definition for the course in terms of the foundations, the axioms of the integers that we will be assuming. So, the axioms of the integers is namely the set Z. Also, this should have mentioned in structures. Z is the reason for the letter C is that this is the German word for number, Zahlen. So when we look at the axioms, we have, it's a ring, so we're assuming all these properties up here, but we're also assuming a relation, namely less than, which we're going to define A is less than B if and only if B minus A is a natural number. And of course, we can see that based on what we know of all the prior math we've had, if we subtract the A over, we have 0 less than B minus A. So B minus A is a positive number. And so since we're working in the set of the integers, it's a natural number. Since the positive integers are the naturals, 1, 2, 3, 4, 5, so on and so forth. And so that's what this difference is getting at, is that B minus A is a natural number. And we have the following 5 properties being satisfied. The transitive property, A less than B and B less than C, imply that A is less than C. Trichotomy, very important, which is we can only have 3 different possibilities. A is less than B, A is equal to B, or B is less than A. Additive property, A, B, and C are integers. Then if A is less than B, A plus C is less than B plus C, which is exactly what I just did over here. Because to go from here to here, we use that property. We do A, and then we take C as a minus A in that notation. And so then we have, this is less than B minus A. And so when we did this, we were actually using the additive property of the integers. And so we can do this. The multiplicative property, A, B, C are integers. Then if A is less than B, and crucial, C is a positive integer, then AC is less than BC. And then we have an order of identities. 0 is less than 1. So a couple of shorthand notations. So we're going to be using A is less than or equal to B. So whenever you use A is less than or equal to B, this means A is less than B, or A is equal to B. Now, what about greater than? We haven't defined greater. Well, we can take A greater than B to mean B is less than A. And so we only need the relation less than. Of course, in practice, we also use less than or equal to or greater, but the key thing is once we have less than, and since equality is a property of the set, we get all that we need. And so these are the axioms that we will be assuming in this course. So next, let's go ahead and take an example, and let's prove this following lemma. And what I will recommend is to pause the video and work this out on your own, where you will prove this only using the axioms of the integers. And so if A and B are integers such that A times B is equal to 1, then either A equals B equals 1 or A equals B equals negative 1. So pause the video, give this a try, and then I'll go ahead and go work through this. So let's go ahead and prove this statement. So I'm going to approach it in 2 cases. Oops, I put 2 cases. So the first case is going to be that A and B are natural numbers. And then the second case is that one of A or B is negative. So let's do the proof. So case 1. So now suppose A and B are naturals. By assumption, we have A times B equals 1. Now what I'm going to do is approach this via contradiction. So towards a contradiction, let's assume that, so we're gonna be negating this statement here. Then either A equals B equals 1 or A equals B equals negative 1. But now the key thing is we're assuming that A and B are naturals. So a equals b equals -1 cannot happen. So we're in the situation where if this is true, it must be a equals b equals to 1. But either way, so now assume that a does not equal 1 or b does not equal 1. That will be our negation of our desired implication here, since we're dealing with positive numbers. So a does not equal b, or a does not equal 1, or b does not equal 1. Without loss of generality, we may assume that a does not equal 1. But if a does not equal 1, what can it be? Well, it's a natural number. So natural numbers are 1, 2, 3, 4, so on and so forth. If it's not 1, the least it could ever be is 2. So in other words, so then 1 is less than a. And so we have this over here, 1 is less than a. So now what we are going to use is the multiplicative property. We have 1 is less than a, and we're going to take b to be our c. So since b is positive, the fourth axiom, axiom 4 of z, implies the following. So we have 1 is less than a. So keep in mind that the 1 is the a and the b is the a. Oops, sorry. 1 is the a, and the a is 1, and the b in the multiplicative property, that's our a, and the b is the c. So if we multiply by then b, since it's positive, we have b is less than a times b. But now we have a problem because the assumption is that a times b is 1. And so we have b is less than 1. But this is a contradiction. Because b is assumed to be a natural number, and the least natural number is 1. But now we are saying that there is a natural number less than 1. And so this is a contradiction, so we are done here. So let's do case 2. Okay, so let's go ahead and do case 2. So with case 2, now we're going to go ahead and assume, suppose one of a or b is negative. And also here I actually mean suppose a or b is negative. So it could be the case that both of them are negative. So subcase 1. So we have two possibilities. So actually, without loss of generality, assume that a is negative, so a is less than 0. So we're going to break this into two subcases. The first one is going to be, suppose b is positive. Now, if b is positive, then the multiplicative property we just used comes to the rescue. So let's go ahead and use that. So we have a is less than 0. Since b is positive, we use the multiplicative property again of less than. And so now we're going to multiply by b. Since b is positive, we can go ahead and multiply. So by axiom 4 of less than, we get a times b is less than 0 times b, which in this case is 0. So we have that AB, which is 1, is less than 0, but that is, of course, a contradiction. So that cannot happen. And so this concludes subcase 1. Subcase 2 is what in structures is called the bootstrap method. So now suppose B is less than 0. Now, if B is negative, then negative A, by assumption, A is negative, and negative B are going to both be positive if we multiply them by negative 1. So negative A, negative B is equal to A times B, which is now, both of these are positive, and then we know from case 1 so AB by assumption is 1, but now we have negative A is positive, negative B is positive, we're multiplying them and we're getting back 1, so case 1 comes to the rescue and tells us that it must be the case that A equals B equals 1, but in this case we need to be careful because it's the negatives. Negative A equals negative B equals 1, which in turn imply A equals to B is equal to negative 1. And so now we are done with this lemma. So let's go ahead and prove the next lemma. So here we have A and B are integers, and what we want to prove is that if AB, the product of A and B is positive, then that is equivalent to both A and B being positive or both A and B being negative. So let's go ahead and do the forward direction. I'm going to leave the converse to you all to do. So assume, let's suppose AB is positive, and we're going to go by contradiction. So by way of contradiction, so contra, that'll be my shorthand for contradiction. Assume, and so now we have to see what is the negation of A and B both being positive or both A and B being negative. And so the negation there is that exactly one of A or B has to be negative. And so assume that exactly one of A or B is negative without loss of generality. Assume that A is negative so that B is positive. And so we have this here. And so now we're going to use the multiplicative property once more. So we start off, so you now use axiom 4 again. So here we have A less than 0. B is a positive integer. So we can go ahead, multiply by axiom 4, that's allowed. This is what I meant earlier. That assumption is crucial, that we know that the C in the axiom is positive. And so we have AB less than 0 is less than 0 times B. But that's 0. And so now we have AB is less than 0, but by assumption, AB is positive. This contradicts the trichotomy axiom. Because we know that only exactly one of the three can happen. A is less than B, A equals B, or B is less than A. But here we have that A times B is both greater than 0 but also less than 0. And so we have a contradiction which allows us to conclude this statement. And so then the converse, I leave it to you. Converse, it's an exercise. It's also found in the lecture notes. So next, let's go ahead and prove the zero theorem. And so this is a theorem we have come to use throughout our math education. So here we have a and b are integers, and what we want to prove is that if a times b is equal to 0, then that is equivalent to a equals 0 or b equals 0. So let's go ahead and prove this. So for the four directions, we're going to assume a, b equals 0. For a contradiction, suppose further that a and b are non-zero. So that is the negation. So the negation of a equals 0 or b equals 0 is that both of them are non-zero. Now we're going to look at this in via cases. So let me put this over here in little one, first case here. If a and b are positive, or a and b are negative, then AB is positive by lemma 1.1.2. So we have just used the previous lemma in here, but that's a contradiction since we're assuming that a times b equals 0. So this is a contradiction. So we know that this situation cannot happen. So now we have, for the second case, so now suppose that exactly one of a or b is negative without loss of generality. Assume a is negative so that b is positive. So then minus a is going to be positive. And therefore, now we have that minus a times b is positive, or just I'm going to remove the parentheses, write this as minus a, b is positive. So now we have 0 is less than negative ab. And now what we are going to use is the additive property. Oops, I meant to laser. So we're going to use the additive property of less than. So now, let's go ahead. So axiom 3. We have 0 plus ab is less than minus ab plus ab. But minus ab is the additive inverse of ab. So here we have 0. And so we have AB is less than 0. But now that is the contradiction we want, since the assumption is that A times B is equal to 0. The converse, thankfully, is much simpler. So for the converse, assume A equals 0 or B equals 0. Then A, so without loss of generality, just to be rigorous here, assume A is equal to 0. Then 0 times B is, of course, 0. And so that is exactly what we want to show. So now that concludes the proof. And so we're done with these three lemmas. And so just to illustrate that with these axioms, we can prove some of the basic notions that we have come to know of the integers. So let's move on to induction. And so these are the properties that we have covered in structures. Now in structures, these are statements that are not proven. And the reason for it is that to prove it, one actually goes through the Zermelo-Franco axioms. And as a result, we will also not be proving the principle of mathematical induction. And so specifically, we have a statement P of n, such that for each natural number n, it is established that if we know that both the base case P of 1 is true, and that for some natural number P of k is true, such that P of k plus 1 is also true, then we get the statement for every natural number n. There's also the principle of strong induction. So we have n naught is a positive integer, and we have P of n is a statement where n is at least n naught. And as with mathematical induction, we have that there's a base case, namely the smallest integer n naught, or I should say natural number. P of n naught is true. And then we know that for every natural number k greater than or equal to n naught, if P of k is true for k less than n, then P of n is also true. And so this was another statement that we covered in structures. And then there's a third statement. There's a bit of lag. So the third statement is the well ordering principle. And so what the well ordering principle says is that any non-empty subset of the natural numbers has a least element. And so symbolically we have that there is some x naught in A, such that x naught is less than or equal to every element n in the set. And so that's what the well ordering principle says. And one of the things that we do in structures is use the principle of mathematical induction to prove the well ordering principle. But the reality is that these statements are all equivalent. There's nothing different, mathematically speaking, between these three. And so that's what we're going to prove now, is the following theorem, that principle of mathematical induction, strong induction, and the well ordering principle, that these are all equivalent. So the way we're going to go about showing this is we can do it in several ways. We could show 1 if and only if 2, and then 2 if and only if 3, and then do 3 if and only if 1. And so oftentimes when proving that things were equivalent in structures, it was more just showing that two statements were equivalent. So we just have to show the if and only if, as we have just done in the previous lemma. But now we want to show that these three statements are equivalent. And if we did it in the same way that we have done before, 1 if and only if 2, 2 if and only if 3, 3 if and only if 1, that's a lot of more work. So instead, we're going to show that 1 implies 2, and then we're going to show that 2 implies 3. And then we're going to show that 3 implies 1. And so, in other words, this here gives the same as that, because then we establish that one implies 2, but then if we go via 2 to 3, and then 3 to 1, and 1 to 2, we have that 2 implies 1. Similarly, 2 implies 3, then we go from 3 to 1 to 2, and so then we have the converse, 3 implies 2. And so this is the way we're going to go about approaching this result. Okay, so let's go ahead and prove that the principle of mathematical induction implies the principle of strong induction. So we assume PMI, and so now we're going to go ahead and construct our statement so that it satisfies the assumptions of the principle of strong induction. So specifically, we have some statement, P of n, where the statement is define for every natural number greater than or equal to some natural number n naught. And so now we have the principle of strong induction at our disposal. So we're going to use that to our advantage. So we're going to go ahead and define a new statement. Define the statement as follows. S of 1 is the very first statement of P, which in this case it starts at P of n naught. And more generally, so we're going to define S of n as the following: the conjunction P of n naught and P of n naught plus 1. And then we're just going to continue adding all the extra P's. Conjunction here. P of n naught plus n, but we have to be careful. Because if we plug in, we want this to agree with our initial terminology of 1. So we plug in S of 1 into this, then we'll have P of n naught plus 1. But we want to get P of n naught. And so we're going to subtract a 1. And so that's the statement. We have P of n naught plus n minus 1. So now that we have our statement, what we want to do is assume the premise of the principle of strong induction. So we have the base case and inductive step, and we want to show that then P of n is true for each n greater than or equal to n naught. So I'm going to go ahead and write these down over here. Just give me a moment. Okay, so here is the premise rewritten. So we're assuming the premise of the principle of strong induction. So we have P of n naught is true, and then for every k greater than or equal to n naught, if P of k is true, for k less than n, then P of n is also true. Now what we are going to do is translate everything back into the statement that we defined for S, because that is the statement in terms of the language of the principle of mathematical induction. So then, this implies that S of 1 is true. Indeed, S of 1, by definition, is P of n naught, but we are assuming that P of n naught is true. So we got that. Now we want to establish the inductive step of this. So now, for each natural number k, if S of k is true, then S of k plus 1 is true. If we translate this, this statement is the same. If S of k is true, this will be the same as the statement. Because of the way that we define S of k, this is the conjunction P of n naught and all the way until we get to P of n naught plus k minus 1. But by assumption, we have that P of k is true for k less than n. This is the premise of the principle of strong induction. So we have that P of n naught is true, P of n naught plus 1 is true, all the way to k n naught plus k minus 1. And if that's the case, then so is, in this case, k plus 1. So here it was for all k less than n. In our scenario, we're looking at n as k. n as k plus 1. So in our case, n is equal to k plus 1. And so we have that this here is true, and P of n naught plus k. So this is the k plus 1 term. Is true. Need some more space. So to recap, the premise of the inductive step, we're applying that. S of k is true. So we're working backwards. This is the intricate part of this statement, is that we're working with the assumption of the principle of strong induction and trying to then mold it into the principle of mathematical induction. So we know that P of n naught to P, so everything all the way to k, so if P of n naught plus k, all of these statements are true. And then the conjunction is true only if every term appearing in the conjunction is also true. So now, what do we have? If when we translate this statement over here, that this is true, we end up concluding then that P of n naught plus k is true. So in other words, this here implies that we can do P of n naught and P of n naught plus k is true. So all that we did was do an extra conjunction with the part that we get from the principle of strong induction, the P of n naught plus k, do the conjunction with what we already had. So we have now this here. And as a consequence, we get what we want because this is the same as S of k plus 1 is true. But now if S of k plus 1 is true, we have satisfied the premise of the principle of mathematical induction. But we are assuming PMI. So now PMI tells us that P of n is true, and so in this case S of n is true. So now we have, by principle of mathematical induction, we have that S of n is true for every natural number n. But now this is saying that the conjunction where we have P of, so now we're going back to P of n naught. So this is saying that the conjunction P of n naught plus 1, all the way to the conjunction with P of n naught plus n minus 1 is true for all n. But I'm going to come over here I'm going to make a little box over here. So I'm out of space. But now if this conjunction is true, that happens exactly when each of the individual statements are themselves true. So in other words, we end up getting, as a consequence, that P of n is true for all natural numbers n, which is what we wanted to prove. And so we have now demonstrated that principle of mathematical induction actually implies strong induction. So let's move on. So next, what we are going to do is show that the well-ordering principle implies the principle of mathematical induction. 2 implies 3. That is done in structures. And in the case that it was not done in your class, I know when I teach it, I cover it. But if it was not done in your class, I do have it in the lecture notes typed up. So please look at that if you have not seen how the principle of strong induction implies the well-ordering principle. So what we are going to do instead is show that the well-ordering principle implies the principle of mathematical induction. Alright, so how are we going to prove this? So we're going to assume the well-ordering principle. And we're going to do something similar to what we just did with the last proof, in that we're going to assume the very first 2 steps of the principle of mathematical induction. And then we want to show, via the well-ordering principle, that then P of n is true for each natural number n. So I'm going to go ahead and write those assumptions down. Okay, so here we have our assumptions. We have that P of n is a statement for every natural number n. And we're assuming that P of 1 is true, and then for each natural number k, if P of k is true, then P of k plus 1 is true. So in other words, the base case and the inductive step. And now comes the beautiful part of this proof. So we're going to create a set. So define J to be the set of natural numbers n such that P of n is true. So, in other words, what we want to show, change the color here. What we want to show is that J is equal to the natural numbers. Because if J is equal to the natural numbers, then that's the same as saying that P of n is true for every single natural number. Because if J is n, then P of n is always true. And so that's what we want to show. So let's go ahead and demonstrate this. Alright, so observe. So by assumption, P of 1 is true. So 1 is in J. So we have this here for a fact. So we know that J contains 1, so it is non-empty. And now, what we are going to do is look at the complement of J in the naturals. Natural numbers minus J. I need to think any more space. Okay, so we have this here. So now, a couple of observations. As we saw, we want to show that J is equal to the natural numbers. So if J is equal to the naturals, then there is nothing to show. So then we have the result. So suppose that J does not equal the natural numbers. Then the set A is non-empty, because remember, we know that 1 is in J. So we're subtracting the naturals from J. So this is going to be n minus 1 at the very least. So we know that that set is non-empty because of that. By the word ordering principle, A is a non-empty set, so we can apply the word ordering principle. It's a non-empty subset of the naturals. There exists some L. So there exists a least element L of J. So let's go ahead and call the least element L. Now, because L is the least element, this means that L minus 1 has to be in J. Or let me just go ahead to not skip any steps. Then L minus 1 is not in A, which implies that L minus 1 is in J. But then that means that if L minus 1 is in J, P of L minus 1 is true. But then the assumption that we have is that if P of k is true, then P of k plus 1 is true. So this then implies that P of L is true, which then implies that L is also in J, but then this implies that L is not in A. But that is a contradiction. And that is what concludes the proof in this case. And so we can conclude that J is equal to the natural numbers, but then this gives PMI. And so now we can conclude the proof and we are done. And so that concludes it for this lesson. And in the next lesson, what we are going to do is go over some terminology and concepts that we covered in structures and do some review of that.